thank you for your, I don't know, just following my instructions. That would be lovely. Okay. So, we're pretty much done with the course. Now, could I ask you to close your laptops? There was one voice talking about possibly looking at the OneNote. Thank you. We're pretty much done with the course. Today's lesson we are going to look at bubble chamber tracks, which will help us with particle interactions. And on our Monday's lesson, we will look at Feynman diagrams, which again, it's not in the syllabus, but it will help us understand particle interactions, okay? We only dip our toes into the standard model. We don't go full head first into it. So, here is an image of a bubble chamber. Now, what they did, they cooled down helium so that it was liquid, so it's really, really cold, liquid helium. And then they start releasing the pressure so that it's just below the double point where any extra energy it would start to boil and turn into bubbles, okay? So it's just below that critical point. And any extra energy it would gain and jiggle a little bit faster and it would turn into a little steam bubble, a vapor bubble of gaseous hydrogen, okay? So, it does that if a charged particle comes racing past. And if that charged particle then interacts with the liquid hydrogen, it gains the energy and turns into a bubble. So you can see all of these lines here. These are all negatively charged kaons, so they've got a -1 charge, and they're racing through this chamber. Okay. Now, could you, if you have your highlighters, now would be a good time to quietly get them out because we're going to be highlighting a lot of stuff. It turns out that there's also a strong magnetic field. And in this image, it's actually directed into the page. Unfortunately, these kaons are travelling so fast, they are actually undergoing centripetal acceleration. The Lorentz force, right-hand rule, is causing them to turn in a circular path, but they're going so fast that we don't really measure it. So it's the slower particles that are going to start to curve. Now, what they found, first off, there's a lot of junk in this image. All right, we're going to highlight the important events, but obviously we've got the kaons streaming through, and these guys are not interacting with any of the protons of the hydrogen, okay? But then we've also got these other spirals here. These are literally called death spirals. These are charged particles that were created by collisions and interactions, and as they start traveling in a circular motion, if they were in a vacuum, they would just continue traveling in a circular path because QBB equals mv squared on r. But because they're in liquid hydrogen, they're losing energy. By creating the bubble tracks, they start losing kinetic energy. And so as V drops, their radius drops as well. And they spiral into death, really. So that's a little death spiral. Now, again, before we jump in this diagram, positive charged particles, right-hand rule, are going to be spiraling anti-clockwise. Negatively charged particles, moving upwards here, negatively charged particles moving up in this image would then spiral clockwise, okay? Now, there's a couple of interesting events, and I'm just going to highlight. If you have a highlighter, pick a colour, and let's go yellow. This event here is that one. Oh, hang on, I'm going to zoom out and cheat and find that V. Sorry, don't highlight that one. Highlight this one, sorry. That one and that one, okay? Now this, obviously I wouldn't be able to know what the hell's going on if it weren't for the key particle interactions of the diagrams on the right-hand side to help us with the image. So what we have here is a proton and a pion negative, okay? They were created. Now, if you look at that, you go, okay, we've got rules here. Conservation of charge. I've got a negative charge and a positive charge, so whatever created these two, they just spawned into existence, must have been neutral. And that is in agreement. There was a charged particle, and we cannot see it, but it's about here. Please don't yawn, that's very rude. And if you can just sort of see what I'm doing, I'm going to highlight this particle over here on our diagram. That was our lambda naught. Okay? Now the key thing with bubble chambers is neutral particles don't leave any tracks because they are not losing any energy to the liquid hydrogen. Okay? So it turns out we had a lambda naught. Now this is a baryon, right? Because have a think. Proton is a baryon. Baryon number must be conserved. So if I've got a baryon number of 1, I've got to have a baryon number of 1. There are no leptons here. We made a proton and a meson. Okay? So that conserves baryon number, it conserves charge. The next thing is momentum. You can also look at momentum. This particle had mass and was travelling with a velocity. So they know its momentum. And so now you've got a momentum of this, and what you'll find in some images, but not this one, they actually track it forward and then start measuring the angles. Because even the momentum of these two new particles, the pion travelling off that way and the proton travelling off that way, must conserve momentum. Okay? Now, next thing, there's so much that you can get from these bubble chamber tracks, and when they made them in the 1930s and 40s, when the standard model was being made, this was the treasure map. This is how they found all of these hundreds of exotic, strange particles. Now, just a second. This sigma naught, it would travel with a certain amount of momentum, so that because they measured the momentum, and so they knew how fast it was travelling. If they knew how fast it was travelling, they can measure the distance, so they know the mean half-life. So they knew how long this particle existed before it decayed. Remember, this is a mean half-life, so 50% would get to that stage, and some might live a little bit longer, some might live a little bit shorter. It's not always a constant value, okay? Last thing on this interaction. It might not look like it, but yes, this proton is curling slightly. Have a think. Proton is much heavier, so it's going to have more inertia. So, and remember our equation, and I'll just recall our equation, R equals mv over qb. Okay? Equal charge in equal fields should have an equal radius, but our proton has more momentum. If the scientists can measure the radius of curvature of these tracks, then boom, they know the momentum, at least relativistic momentum, and then they can do all of the relativity stuff and figure out how fast it's travelling. Now, conservation of momentum would then, the remaining momentum must be the pion. Now, the pion is a meson, it's the middle, it's a quark, up quark, anti-quark, what is it? It's an anti-up-down quark, a little bit less mass. Okay, so they're doing this, they're picking all of it apart, figuring out mass, velocity, radius, momentum, and it's all agreeing. These laws are being conserved. Yes, Mr. Rahal?
Those two angles are the same.
Those two
angles are the same.
No. No, they would be in such as to conserve momentum.
So they're not the same?
No.
Why not?
They would be in such a way so as to conserve momentum.
How?
A heavier particle would have less horizontal momentum than a lighter particle. Ah, okay. I'll leave that as a statement. Now, underneath, I have highlighted, here it is here. There's the interaction. Now let's go back to this. Okay, we will come down. I'll let you copy this down in just a moment. Let's look at a few other interactions. What caused this? Well, it says at the top, it was up here, a K minus meson interacts with a proton and produces these guys. So I'm highlighting this with my pink pen. Here's my kaon beam. Okay, and you can see lots of other kaons that were travelling in the same direction because perhaps, George, perhaps they were all being accelerated by the same LINAC or the same cyclotron, and then they were all allowed to enter this same region. Okay, so they're all travelling parallel with roughly the same amount of speed or velocity. Then it says somewhere here strikes a proton. It then produces an omega minus. It produces a K naught, and it produces this guy up here, K plus. Let's just follow him. Where's he going? He's going all the way up here. All right, there you go. So, Let's try and replicate that on the image. We've got here, and then now the K0 doesn't leave any tracks. Don't worry, that's just my beer cooling for drinking it at the end of the day. Here's our tracks. Follow these tracks if you can. Okay? Now, let's go back to Mr. Rahal's question. How do they know that this K0 went that way? Well, it's conserving momentum. They would have said, we've got a sum of momentum in this direction. If the other particles are observed to have so much momentum right, then our K on neutral must have so much momentum left. Zach? And Toby, are we all in agreement? Good. Yes? If you've got your laptop up, I hope it's because you're doing physics. Good. Next, you go, well, how fast was it travelling? Well, let's conserve energy and mass equivalence. I know how much energy my detected particles had. I know how much my K-on negative had at the start. So this particle going in that direction must have this much energy, and so it must have gone this far before it decayed. And unfortunately, well, maybe it kept going, or maybe it decayed. What it decayed into maybe wasn't detected. But that's how they go. They don't just go, oh, just draw an arrow that way. No, they measured it to have that angle and that length. Okay? If we look down here, we've got our, there it is there. That's the interaction that started all of this. But there's a couple more. The omega minus, if you have a third coloured pen, the omega minus then didn't travel very far. Look at him. He went this far. Okay? Travelling at very fast. It decayed very quickly. These particles are all travelling up in the order of 0.8 to 0.99 C. These are all very, very small particles travelling very, very fast. Remember what Richard Feynman said. To make these things, we've got to smash really small particles at very high speeds to make the correct mass energy equivalence to produce these heavy particles. So these guys are all travelling fast. All right? And so if you measured it literally travelled 1 centimetre, then you can figure out that it had a mean half-life of 10 to the negative 12 seconds or something. Before he went and made a pion, and this weird character, neutral, I don't know, that's a capital Greek character, maybe epsilon. Yes?
No, it's a Z.
Z.
No, Chi.
Oh, that's right, chi.
Yeah.
Thank you, our Greek representative. So the omega minus, it's a baryon, decayed into a baryon, and a meson. That's allowed. Baryon numbers conserved. It was negatively charged. Neutral and negative. That's allowed. Let's just highlight that on our map over here. There he is. That goes off, and then, or does it kink, or does it? No, apparently it keeps going. We don't see the sigma, but he must have been there. Okay? All right, let's highlight that down here. There he is. Last one, that was, okay, now let's follow our sigma. At this intersection, oops, I wanted that to be red and it is not. Oops, and now it's doing that. At this intersection, what does our sigma do? Well, it decayed into that lambda naught, but also 2 gamma rays. Final highlighter. The sigma decayed into a gamma ray, and our, look at that, a neutral baryon decaying into a neutral baryon.
So which one's the sigma?
The sigma, oh, did I say, I think I called him, what was it, Chi?
Yeah,
Chi.
so.
Okay. All right. Again, where is this? Well, okay, guys, watch the screen now. This is important. We know that gamma ray was there because then it did a pair production and produced, wouldn't you know it, a positive and a negative, possibly a lepton and an antilepton. And the reason why I know that they should be equal mass is, oh, hang on, they've got different curvatures. Damn it! I was going to say they were equal curvatures. That was a gamma ray. Neutral, lepton, no, sorry, not a lepton, lepton, antilepton. Okay, so there's so much stuff going on here. We know that was there. And then follow this again. There's another V up there. And again, some particle and then a death spiral. Okay? So lots of stuff going on. But that's the whole thing. if you see a V in a bubble track, it means there was some neutral particle travelling to that intersection and then decaying. Okay? And so you have to think, these poor physicists back in the 1930s and 40s have got this, and they're going, holy crap. We've got a neutral particle, figure out its momentum. All right, it's travelling that way. All right, now we've got over here momentum. All right, follow it back, conserve momentum. All right, there must be an intersection here. They're doing all of the math. Momentum, energy, mass, relativistic effects even. They're doing all the Lorentz stuff. All right, so this is getting tricky. But for you lot, at year 12 level, I would like you now to show that these are conserved using those four fundamental. In fact, here's the problem. Normally when I do this activity, gentlemen, Jake,
Yeah.
we've got all of these conservations and they work, and then we get to one last image and strange number is not conserved. And this was an issue. They found this weird bubble chamber tract that the model couldn't answer. And I'd like it to be page 20. Unfortunately, I think a couple of these don't conserve strange number. Please do not feel scared or anxious. There is one boson interaction where strange number is not conserved. So, at the very least, in the Year 12 syllabus, you should be able to show me charge, baryon, and lepton number. Okay? So, I'll give you a couple of minutes head start. For your convenience, I have given you the quark constituents. These are on page 8 of your booklet in the yellowy red table. But they're there. Again, just recall, guys, you're not expected to remember the quark constituents. If you were given a question with any heavy baryons or mesons, you would be given a table, or you would be told that they are made anti-up strange is your K minus meson. Okay, you're not expected to memorize any of these. Okay, I'm going to play catch up now. So, -1, +1, -1, 0, +1. All good. Not a baryon, is a baryon, is a baryon, not a baryon, not a baryon. All good. Lepton. No, 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 no. All good. Strangeness. -1, 0, -3, +1, +1. All good. Okay?
I had it right the first time. It's C.
Chi.
C.
C. C. Okay. KSI. Okay. -1. Naught. -1. All good. Is a baryon, is a baryon, is not a baryon. What? What's wrong?
You are too fast.
No, well, you should be... Get on my level.
I'm trying to write down the actual...
Okay. Now, these questions are not going to be worth many marks. It's not going to take you more than a minute or two, so you're not expecting it to be worth more than a mark or two to show that lepton and baryon and charge is conserved. Okay? Baryon, gamma ray, not a baryon. Delta naught is 2 gammas. Yep, remember from the...
Why is strange number?
Hold on, Justin. Back to Palandri. Palandri. We saw there were 2 gamma rays because there were 2 V's that were produced.
And why do they have to be on either side of the equation?
What? There are... No. We are looking at this particle interaction here.
Yeah, yes.
Reactant, product.
Why is it on either side of the lambda?
I don't know, to conserve momentum. You can't just have 2 gamma rays flying off that. Oh, because I just decided to put them that way. Stop being so pedantic.
Can you do it another way though?
You could put gamma plus gamma plus... Yeah, there is no rule as to how you present your symbols.
Yeah.
Justin, you were going to say something.
So
So why is strange number important?
Because when the W gauge boson is involved, strange conservation is violated. But we'll look at that on Monday. Okay, so for now, just put a little... it's not in the syllabus. But for now, just put a little upset face. Okay. We'll look at that later. Guys, are we all on the same? Are we all at the same time? Here we go. Charge 0. Protons +1. Pion negative. Is a baryon. Is a baryon. Is not. None of them are leptons.
And then it goes from -1 to 0.
Whether the up arrow thing is a barren that is doing a big job.
You'd have to. You're right. Some of these Greek symbols, Ben. Gentlemen, the question has been asked, how do you know it's a baryon? If you were just given a Greek symbol, you won't know because some mesons will have Greek symbols and some baryons. You would have to look at look, 3 quarks. It's a baryon. If you saw a quark antiquark, 0 for baryon number. So for example, quark antiquark has a baryon number of 0. 3 quarks is a 1. Okay? And leptons, you need to know electrons, muons, tauons. And they're neutrinos. Well, it's in this. You've got a standard model poster in your data sheet. Yes. Okay. Are we okay with that?
Mesons don't have a barren number or electron.
Correct. But they're hadrons because they're made of quarks. And they obey Fermi-Dirac statistics unless they're acting as bosons. So mesons are weird. That's the whole thing about this, guys. There is no black and white rule. Stuff gets weird. They find strange things. They have to tweak the rules. That's the whole thing with castling and... Eric Pan said some French word about a chess rule that I wasn't aware of. There are weird rules. The more you observe the game of chess, there's more and more strange rules. Okay? So, and we're just having a few glances at a few of the first moves of chess. Alright? We don't have to play the whole game. We're just looking at some of the basic rules. Okay, over the page. I am going to highlight part D because we can do that. Here is D. A kaon neutral, there he is, decaying into 2 mesons. That's it. I've just highlighted that blue. So, I didn't really give you much room underneath. Apologies for that. 2 minutes. Copy down the particle equation, copy down the quark constituents, and then show that at least the top 3 are conserved in this interaction.
Is it anti-strange?
It has to be because strange has a charge of minus 2/3. No, wait. Anti-strange is, plus 2/3. Wait. Strange is minus 1/3. Anti-strange is plus 1/3. So plus 1/3 with the down minus 1/3 gives you 0. Okay, sorry, I got a little bit confused there. Okay, I'm catching up now, guys. Let's get writing down stuff in, please. Shush. What do we got? 0 goes to minus 1 plus 1. That's allowed. No baryons present. That's allowed. No leptons present. That's allowed. This is just a meson decaying into 2 other mesons. Okay? Strange is strange. Okay? All right. Next one we can have a look at. F. Let's highlight F, the decay of a pion. Okay.
No one knows.
Yes, it is allowed. Hang on. Wait a second. Wait. Did we observe it occurring in nature? Then yes, it is.
So maybe the straight
That's it.
rule doesn't work.
We've already joked about this. There is an exception to the strange conservation, and we're seeing this. I'm going to explain it on Monday. If it's observed in these bubble chambers, then it must be allowable. Okay? So we're just proving this. For part F, here is F like so. So can we draw that in, please? I think that was F. It says it was. In fact, I highlighted it for too long. There is our first particle that then splits off at that vertex into a positive and negative. Because they're spiraling in different directions. One must be positive, one must be negative. This one didn't last long enough for us to observe it curving, but... Oh, hang on. Wait. And then, subsequent decay. Okay, so... Well, maybe not highlight that, but just show that this can be done. Yeah, I don't think that's the right particle interaction. Let's show that this can be done. That is not an antipositron. So, get your vocab correct. Okay. Come on, guys. Toby, you got this written down? Oh, no. So you're just talking. Well, I want everyone to be writing and you're having conversations. So just pretend, like motion with your hand. There we go. All right. Over the page, please. Now, I'll leave this for you guys to do on your own, but you should be able to identify I, which I think we just did. You should be able to identify L and K. But we don't have much room on this page. So let's go over the page. This one's good. We'll look at this one here, okay? Over to this page, please. Okay, this one's quite fun. We've got a neutrino beam. Again, this was a big deal because neutrinos, as we know, are very weakly interacting. They don't often collide with nuclei, and so this was quite a good event. There's a beam of neutrinos coming through here, and for most of this bubble track you'd see nothing because they'll just zoom through 20 light years of lead without colliding. So they were able to capture that it smacked into a proton. So we've got a neutrino interacts with a proton, okay? We don't see the proton, it was just sitting there minding its own business being liquid hydrogen. And then look what we got. We got a proton over here. We got a pion here, and then there was a kink, which is telling us that there was another action, another event. So we'll just highlight that. Then a muon positive, a pi positive, a muon negative, and a K negative. There was a kink there. Okay? No, the kink was because out spat a little neutrino. To conserve lepton number, that must have been a mu neutrino that went flying off. Okay? Again, not interacting so we don't see it. So that's the whole thing. If you see a kink in your spiral or curve, that means that momentum has changed. If momentum has changed, it must have been that a neutral particle has been ejected to conserve momentum at that point. Okay? So again, that little kink, which, I mean, you can barely see it in the actual image, it's definitely been kinked, so some particle is shot off. All right. All of that, now, apparently, another big thing was there was an excited D meson. See this excited D meson? it's not actually visible. Because if we look at what's happening, it says here's our neutrino striking with a proton in the equation. And then it just goes, that then went proton, muon, pion, kaon negative. And those are the 1, 2, 3, 4, and kaon, pion, proton. Kaon, pion, proton, muon. Yeah, that's it. But we didn't see that. So something was going on here, and that, I mean, if you Google searched excited D meson, it probably lasted for like a femtosecond and travelled a micrometer before decaying. So I'm not sure how they detected the excited D meson, but let's just ignore the existence of the D meson. And now look what we got. Whoa, here we go. Now, while you are scribbling that down, I will write in the quark constituents. K minus is anti-up strange. Pi plus is up anti-down. Okay, there you go. So now, guys, look at this. From that, you can identify which of these are baryons, which of these are leptons, and which of these are mesons, because the leptons aren't made of quarks. All right, so we've got a lepton starting, colliding with a baryon. And it must have been travelling so fast because it was able to make heavier stuff. And we know that neutrinos are very light, so it must have just been travelling 99.9999999% the speed of light, so that it had energy by virtue of its... It had energy by virtue of its energy. It had energy by virtue of its really fast speed. Okay, let's get going. Actually, I don't want... let's bring it to the top. Don't ignore that bottom one. 0, plus 1, minus 1, minus 1, plus 1, plus 1, plus 1. That's allowed. We have a net plus 1 charge on the left-hand side. We have a net plus 1 charge on the right. Lepton number. We've got a lepton. We don't have a lepton. We don't have a lepton. We got a lepton. We don't have a lepton. We don't have a lepton. We don't have a lepton. That's conserved. Not a baryon. Is a baryon. Not a baryon. Not a baryon. Not a baryon. Is a baryon. Not a baryon.
Will we always be told what the...
Cast your mind back 10 minutes ago when I said you don't need to remember the quark constituents of all the heavy exotic ones. You should know proton and antiproton, neutron and antineutron. If you were given one of these in a test or an exam, you would have to be given it in a table or told. The kaon plus is anti-down strange, or whatever it is. I don't know. Strange anti-down. No, up anti-strange. Lastly, not strange, not strange, is strange, not strange, not strange, not strange. Oh no.
Wait, why is that minus 1?
Why is what? Because strange quarks have a strange number of minus 1.
Then what is an anti-strange number?
Plus 1. It's all in the table on page 8.
Why do they not? Why does it make strange numbers -1?
Now, I'd also like us to consider, what would I like us to consider? What does that kaon minus do that when it decays? Here we go. Looky here. Looky here. It decays into a sigma minus. No, it doesn't. It crashes into a proton. Why have I... Hang on. Have I missed... Wait a second. Which kaon minus am I looking at here? There. Oh, okay, here's what I did. Sorry, I'm back on it now. We could say this kaon minus then collides with a proton that was sitting there minding its own business being liquid hydrogen. It then decayed into those two particles. Okay? So here's the problem. You would look at that and go, oh, this kaon just turned into 2 pions. One might, but that would violate certain rules. What's actually happening here is the sigma is made, the pion is made, and then the sigma goes, no thanks, I'm going to turn into a neutron and a pion. So, shh, stop talking. This pion was made with the sigma, and this pion negative was made with the neutron. Two separate interactions, but they look like they came from the same vertex. Okay? So let's just be careful. I can't really highlight the sigma because something's telling me that if I Google search sigma minus baryon, it's going to say it lives for 10 to the negative 13 seconds and hence travels nowhere. It travels like a millimeter. And so a vertex is going to be shifted by a millimeter and then makes its own particles. One of them a neutron, so we don't see the... Oh, but look, they've said, conserving momentum. So let's look. The pion negative started travelling up, and so neutron travels down to conserve momentum. Look at that. Pion travels up, and whee, see you later. Neutron travels down. There we go. Okay? Meanwhile, this sigma, whee, okay, so again, it's tricky. These poor scientists back in the 1930s and 40s looking at this going, it's like watching a game of chess, and we've got to make the rules. We don't have the rule books, all we can see is a chess piece moving around the board. Crazy stuff. By the way, you could do this one as well, but let's not, because I want you now, last equation, here. There we go. Do that, please. And if you finish, maybe jump on Google and search for me the sigma minus baryon, because I'm keen to know how long it lives for. Maybe Toby could do it, because he's got no booklet. Well, it's going to go up. So you do the sigma minus baryon. Woof. Oh. Okay. Okay. If it was observed to travel that far, it mustn't have been traveling very fast. So maybe it didn't have much mass energy. Always interrupting my lessons, Mr. Rahal. Always. No. No. Oh, at least strangeness is conserved. That's nice. Turn the beat around, up, down. What song's that, Zach Jacobson? Up, down, turn around.